whole bunch of matter, okay? Especially the bulk material. When we say bulk material, we mention that for example, the physical state of matter, or pressure, temperature, volume, all these. Excuse me?
Kaydı başlatmayı unuttunuz hocam.
Okay, I am starting.
Hocam ben kaydetmeye başlamıştım.
Somebody has started already, so that's fine. All right, thank you anyway. Arkadaşlar, presentation'ı bakarken bu ekranı göremiyorum. Sadece bir tane ekranım olduğu için maalesef. Onun için bunu indireceğim. All right, let's continue. What is a physical state? Physical state of a sample of substance is its physical condition is defined by its physical properties. Okay, so we need some variables to define or to specify the state of the system. Those ones are amount of substance, we give with the symbol N, the volume it occupies, which is the symbol V, capital V, the pressure, small letter P, and the temperature T. These are the four main variables that are absolutely needed to specify the state of a system. Okay? So, in order to describe a system fully, without any missing parameters, we have to have some macroscopic properties. And we also need to know whether this system is homogeneous or heterogeneous, or it includes one component or more components, and if the system is actually in equilibrium state. What I mean by equilibrium state is I will just tell you in a bit. So these variables that define the state of the system, physical state of the system, are called state variables. Okay, one of them is pressure. Okay, so the origin, how does the pressure is formed? The origin of the force exerted by a gas is the incessant battering of the molecules on the walls of its container. So when we have gas molecules or any other material inside a container, okay, the molecules will hit the wall of the container. That hit, that collisions create the pressure. That's the molecular origin of the force, okay? The origin of the pressure. So the pressure is defined force over surface area. Force divided by surface area. And some units of the pressure are Pascal, which is the SI unit, is given by 1 Newton divided by meter squared. Okay, and there are some other pressures that you should actually know. When we talk about the standard pressure, we just show P and 0 with a bar on it. Okay, that shows the standard pressure of 1 bar pressure. So when we have a system like this on the scheme over here, when we have initial system which is not in equilibrium, if we have a movable wall, everybody by intuition should know that the pressure will flow from high pressure to low pressure, and the system at final stage will reach to equilibrium. So this kind of equilibrium is called mechanical equilibrium. Okay, this is what we have told in the last class. As a second variable, the temperature, that property determines in which direction energy will flow as heat when two samples are placed in contact through the thermally conducting walls. So the pressure is formed by collision of molecules and will flow from one higher pressure to lower pressure, and the temperature is formed by actually the motion of the molecules, the speed of the molecules, or the velocities of the molecules, and that will actually flow as heat from hot to cold region. Okay, when you have a system in which two conducting container touches to each other, if one is hot, the other is cold, everybody by intuition know that the heat will flow from hot to cold. This is called common sense. And at final stage, both will have the same temperature, And such kind of system is called at thermal equilibrium. The system is at thermal equilibrium. Okay, so there are different types of temperatures measurements that actually we talked in the last class. One of them was Celsius scale, which is actually a relative measurement of the temperature. By saying relative, I mean it's going from plus to minus regions, and the increments is actually the same as the Kelvin scale, but the Kelvin scale is actually absolute temperature, which means there is no negative Kelvin temperatures. Okay, it starts from 0, it goes up, just like just in the order of Celsius degree. Okay, so when we want to convert from Kelvin to Celsius, we use this formula right here. So sometimes we say the temperature, the Kelvin temperature, as thermodynamic temperature. Okay, just because thermodynamically it is not possible going below that point, going below 0 point. Okay, this is a second variable. What about third variable? The amount. The amount of substance is actually the number of is a measure of the number of specified entities present in the sample. Okay, so amount of substance is a general official name of the quantity, but it means different variables, like for example mass, or number of particles, or volume, or mole, Avogadro's constant, and molar mass. They are all related to amounts. Okay, so amount actually will have, just like temperature and pressure, amount also flows from one side to another depending on the condition of the system. If you have a non-reacting system is right here. Okay, so when you have, for example, water liquid and there is nothing above it, so everybody knows that some of the water will evaporate until it reach to the gas form, so that the liquid and gas form are in equilibrium. This is called phase equilibrium. Okay, so the matter from liquid side flows to the empty side. That is continuing until it reaches to phase equilibrium. If there are multiple reactants and the system is reactive, then they actually react to form some products. And actually, this is also an example of flow of amount. Amount will still flow until the system reached at the chemical equilibrium now, instead of phase equilibrium, because now the matter will form another new materials that will to the chemical reaction between them, and in the final case, so A, B, C, and D are all coexist in the system, which is at chemical equilibrium. Okay, so there are now, we have defined 3 of them. So when we actually summarize state and equilibrium, so equilibrium is a state of balance. It can be a thermal equilibrium, which means no further temperature change throughout the system. It can also mean mechanical equilibrium. That means no pressure change throughout the system. It can also mean phase equilibrium, system having more than one phase. The masses of each phase is at equilibrium. And chemical equilibrium, the chemical composition is actually does not change over time. That means that means the chemical equilibrium. Okay, to define the system of state of the system. Okay, when we want to describe a system, state variables, especially pressure, amount, temperature, and volume. So when you have a system at equilibrium, okay, the system is actually independent of the history of the system. It does not mention, or it does not need to know which path it took to come to that, to reach at that point. It does not care which path it took for a state of a system at equilibrium. Okay, if you have a system at equilibrium, a state of the system, then you don't need to know which path or which way did it take to come over there. It only cares about these macroscopic properties that describe the system. Okay. So do we need actually all of these variables? No, we don't actually need all of them. We will actually reduce some of them by introducing equation of state in a bit. But we should also know that we have talked in the last class that there are some two properties of amounts. The extensive property, which means amount dependent, which also means the value of it is changing by increasing the size of the system. Okay, for example, mass, volume, mole, energy, etc. There are other thermodynamic properties that are extensive that I haven't written over here to not to confuse you. There is also intensive properties. These are independent of amount. Okay, so the system, by changing the size of the system, the value does not change. So an example: pressure, temperature, concentration, density. And we also said that some extensive properties can be expressed as intensive counterparts. For example, volume is an extensive property, but molar volume is an intensive property. Mass is an extensive property, density is not. Density is intensive. Mole is just like we said, is an extensive property, but the concentration is not. Okay, so we can actually switch between extensive to intensive to describe the system more accurately. So this is very important because sometimes you need to describe the system in a way that requires no further knowledge. So if you use extensive properties, you must also give with what amount you're talking about. Okay, if you are giving a value of any variable, then that is extensive, then you have to mention what amount you are talking about. Okay, if you are giving intensive property, what you need to know is just the unit of it. What is the unit? That's the only thing that matters. So it does not really, you don't need to mention about the size of the system if you are talking about any intensive property. Okay, so we also reminded you that some macroscopic observations, which is also called gas laws, that correlates state variables to each others. Okay, we said there are 4 different variables at least that actually need to be known to define the system state of the system. But there are some experimental facts. For example, Boyle's law. It says that if you keep amount and temperature constant, P times V, or pressure times volume, will be constant. So that's actually one equation that reduces a little bit about the required knowledge about state of the system. The Charles law, we also said that if you keep amount and pressure or amount of volume constant, the volume is actually temperature linearly dependent to temperature, or pressure is linearly dependent to temperature. These are examples of limiting law, which means that a law that is strictly true only in a certain limit, in this case, as pressure goes to 0. So these observations are only valid for perfect gases, okay, or ideal gases. But for real gases, when the pressure goes to 0, they behave just like ideal gases, and these observations are also valid for real gases when the pressure goes to 0. That is why these laws are called limiting laws. Okay, so Avogadro's principle, when the pressure and temperature is constant, the size of the system will increase with the amount of the system. The volume will linearly depending on the number of moles. Okay. When we look at the Boyle's law in detail, we see that the plot pressure versus volume will go like this. This is not a straight line because the multiplication of pressure with volume is constant, not just P over V. Okay, that's why we see plots like these. To different temperatures. Okay, at each temperature, each one, for example, for this one, the temperature is constant. This one is temperature is also constant, but at a different temperature. Okay, since these are all at constant temperature, we call these an isotherm. Okay, an isotherm means any plot, any graph that has the temperature constant. Okay, when we actually reverse the volume as 1 over volume, we see that pressure versus 1 over volume now correspond to a perfect line plot. This is just another way of writing PV in terms of P times 1 over V. Okay. So as you see, all of the temperature values, when we increase the temperature, the slope will increase. But very interesting thing is that when we lower or extrapolate pressure to go to 0, when we extrapolate pressure at 0, the volume is also going to 0. Okay, and all of the temperature values are all converging at 0 to 0 point, 0, 0 origin point. Okay, this will tell us something very interesting in especially Charles' law. When we look at Charles' law, the temperature, in this case, in the first law of Charles, the volume is constant. Okay, for each plot over here, the volume is constant. This is one. This is another one, volume is constant, but it's a different volume, okay, different size system. So when we decrease the volume of the system, the slope will increase. But interestingly, when we extrapolate again, all of the volumes, the temperatures are converging at some point. That is why we call this a thermodynamic temperature, or yes, that's why we call this thermodynamic temperature. So when you decrease the pressure to the 0 bar, this lowest point, the temperature will also merge at 0. Remember, when you have Celsius scale, you did not have that. Celsius scale could go below 0 point. But now, as you see, there is not, you cannot have negative pressures. That's why the system, all of different volume values will end up at the same exact temperature when the pressure goes to 0. This is why this is called limiting law. And actually, when we have volume constant, we call this plot as an isochore. Okay. The second law, second Charles law, says that when the volume and mole numbers constant, then pressure is linearly dependent to temperature. Let's look at this graph. As you see, the same exact relation as this one. Now, instead of volume, we fix the pressure. Okay? In this case, we fix the pressure and see how volume changes with temperature. It's just like the pressure case, where we decrease the system to 0 volume, we cannot have negative volumes. All of the temperature values at different pressures will end up at the same exact point, which is called thermodynamic temperature. So when you have a system with constant pressure, any graph that has constant pressure is called isobar. Okay, these terms are very important, and you are going to be asked in the exams. Are you with me? Is everybody okay and listening to me?
Buradayız hocam.
Is there anything that you understand? Okay, let me show the participants. Let me ask a question to Ceren. Ceren Çakıcı.
Efendim hocam.
Okay, let me ask, what is an isobar mean? Isobar.
Basınçları eşit olan sistemler.
Okay, when I ask questions, ladies and gentlemen, please try to answer in English. This class is in English, okay? And you took English preparation classes. So you are listening in English, so you have to also speak in English. And when I ask questions on exams, I will be asking you in English and awaiting your responses in English. Okay. Doğukan Bilge. Do you listen? Doğukan Bilge is not here, although he turned on the computer. Elif Taşkın. Okay. Elif.
Evet hocam.
Okay, can you tell us whether the temperature is extensive property or intensive property?
I can't say it.
We can barely hear you. Please volume up.
Hocam intensive.
Intensive. Why? In English, please. Okay. When we increase the size of the system, for example, we have a glass of water. We dropped some of them. Is the temperature changing or not? It does not change. That's why we call this property as an intensive property, right? Okay, what else? Kader. Kader Yıldız is not here. Okay, I am going to ask to Gözde Balçık.
Evet hocam buradayım.
Harika. Please try to speak in English. Tell me how the pressure is formed. What is the origin of the pressure? Why we see pressure? How does it form? Yes.
Pressures form, değil mi?
Yes.
Gas form.
It doesn't have to be gas. If you have a liquid system, you still have some pressure, right?
Yes.
So how does the pressure form?
I don't know.
Can anyone answer? What is the origin of the pressure? I need an answer. Okay, should I pick? There are so many Elifs, so I will ask to Elif Sude Karan. She is not here. Okay. So some people turn on their computers and leave it, or what? Anyway, this is not fair. Okay.
I'm here.
Thank you. Can you answer to question how the pressure is formed? What is the origin of the pressure? Why we see pressure? Why we measure pressure on substances, on matter? What is the background origin of it?
I don't know.
If you can answer in Turkish, I accept.
Hocam soruyu tam anlayamadım.
Basıncın kaynağı nedir?
Basıncın kaynağı.
Neden basınç oluşuyor?
Yani hacimle alakalı mı? Bilmiyorum.
We talked actually about it. Okay, Jaylin Karatepe.
I'm here.
Can you tell us why we see, we observe, we measure pressure? What is the origin of it?
The origin of it in atomic scale actually force exerted on an area, and we measure for interpreting the systems and equilibrium maybe.
Okay, let me ask this then. How does the force formed? What is the driving, what is the origin of the force?
energy, it can be said.
No, the force is actually formed by collision of the molecules on the wall. Okay, the
That's
molecules will hit the wall of the container, and that will create a force. Since this wall has a surface area, the force over this surface area divided by this surface area is actually the definition of the pressure already. Okay.
It can be said then it's from a motion.
Yes, it is still from motion, but the main point here is that the molecules will collide to the wall of the container. That is how the pressure forms.
Okay, I see. Thank you.
Yeah, how about temperature? Can anyone answer to temperature? The origin of temperature. What is the origin of temperature? I don't see any hand raise, so I'm going to ask someone. Okay, there are some. Okay, Doğukan and Kader, I saw your text. I accept. But I will ask to someone else then. Ezgi, Şengül. There are two Ezgi's. Ezgi Şengül, are you here?
Buradayım hocam.
Great. How do you think the temperature is formed?
I don't know.
Very nice answer. And
I have
very
no
honest.
idea.
Okay. Can you guess at least? Okay, you don't, ladies, gentlemen, you're not, I mean, this is the first time you are taking this class. You don't have to know exactly. So you can guess. Feel free. Don't be obsessed. Okay? Just like you're talking to your friend, be very relaxed. I mean, you don't feel pressure on you. Please. I want to do this more interactive because I don't see you and I don't know whether you are actually on your computer following me or not. That's why I want some at least response from you that the class is being listened. Okay, the pressure, the temperature, the origin of temperature is still the motion of the molecules. Okay, it is about the velocities of molecules, the kinetic energy. You remember 1/2 mv squared, and that is the origin of the actual temperature. Okay, according to Newtonian mechanics, classical mechanics. All right. So let's continue actually to where we have left. If you want, we can give a break of 5 minutes and then we can continue. All right? Okay, right now 10:20. We will be here at 10:30. I will start at 10:30. If you are on time, if you come on time, I will finish very soon. Okay? Arkadaşlar anladınız mı?
Evet hocam anladık.
10 dakikalık
Evet
break veriyoruz. 10 dakika sonra burada buluşacağız. Eğer zamanında herkes gelirse 10.30'da burada olursa son dersimiz olmuş olur muhtemelen. Belki de erken kapatırız. 11.30'da kapatmış oluruz. Tamam. Şimdi ben sessize alıyorum ama durdurmuyorum yayını. Siz de öyle yapın. Kapatıp tekrar bağlanmayalım. Kayda devam etsin. Görüşürüz arkadaşlar. Merhaba arkadaşlar. Herkes burada mı? Umarım herkes buradadır.
Buradayız hocam.
Tamam, çok güzel. Şu anda ekranımı 2'ye çıkardım arkadaşlar bu arada. Umarım daha iyi olacak. Şuradan share ederek screen 2'yi share edelim. Evet. Şimdi sizi de burada aynı anda görebileceğim diye ümit ediyorum. Evet. Hem sizi görüyorum hem ekranı. Güzel. Şurada hatta chat'i de gösterme vardı. Onu da açayım. Şimdi. Neyse. Chat'le participant aynı anda gösterilmiyor. Neden gösterilmiyor? Tamam arkadaşlar. Devam edelim. Nerede kalmıştık? Size sorular soruyordum. Arkadaşlar hızlıca tekrar üzerinden geçiyorum. Basıncın kaynağı dediğimiz gibi kuvvet. Yani kabın, konteynerin çeperine gaz moleküllerinin çarpmasıyla oluşan kuvvet. Sıcaklığın kaynağı ise gaz moleküllerinin rastgele olan hareketleri ve o rastgele hareketteki hızları. Madde miktarını da söyledik. Evet, dengeyi de söyledik. İntensif özellik değişmeyen madde miktarıyla değişmeyen, ekstensif madde miktarıyla değişen dedik. Boyle's kanununu gösterdik. Evet, burada kaldık arkadaşlar. Let's continue in English now. Okay, now, in principle, to describe the system, we must know at least 4 variables, the state variables: pressure, volume, amount, and temperature. Experiments, as we have seen in the Boyle's charts and Avogadro's principles, show that these 4 variables are actually interrelated to each other. Okay, they are related to each other. And there is one equation that actually that combines all of these variables together in one just single equation. And this equation is called equation of state. Okay, so equation of state is shown as, for example, one of the variable as a function of the other 3 variables. We chose P over here, but we could we could choose volume as a function of temperature, amount, and pressure, and we could just pick another, just temperature. Okay, so this can be defined as that there is one single equation that actually includes all these 4 variables, which also means that all of these four variables are not completely independent variables. One of them must be dependent on all other 3 independent variables. Okay. In here, you can see the pressure is dependent variable, and temperature, volume, and amount are independent variables. Okay. So this is dependent variable, independent variables. All right. So for perfect gases, we can actually combine all these Boyle's charts and Avogadro's laws in a single formula, which is going to give us PV equals constant times NT, which is just like over here, what we said, all 4 variables are in a single equation. So this creates an equation of states. Okay. So in this case, since all these observations are for perfect gases, So the equation of state belongs to the perfect gas or ideal gas. What we call, in short, this is ideal gas law. Okay, and the constant over here is given by R value. Okay, so as you see, P is a function of N, T, and V, and the R over here is a gas constant, ideal gas constant. And when we look at the R, there are two common units of it. One of them is using these unit system. You get 0.088822 liter atmosphere per mole Kelvin. Or you can just use the SI unit system, and you can get 8.314 joule per mole per Kelvin. Okay, so these are the two units of the gas constant. This is what you have to know. Okay, you have to memorize this one. I will try to ask question about this conversion from one to another. So, okay, what is more is that when mixture, instead of having just single component, now we can talk about the partial pressure of each gas in this mixture. The partial pressure of each gas is just like that gas alone fills that whole volume alone. So this is called Dalton's partial pressure law. Okay, and it is given by any component's partial pressure is the mole fraction of that component times total pressure of the system. Okay, and actually when we combine PA, PB, all PJ values, we end up with total pressure. This is still valid for perfect gases. Okay. Yes. Question, Bora.
Sorry, I was busy. You can repeat the question. Bora, you say Bora? Yes.
Dalton's partial law, pressure law. Is that? Yes, Bora. You raised your hand. Please ask question.
I don't raise my hand.
Okay.
Ya ismimi söylediğinizi zannettim hocam.
Ha, tamam. Yok, ben burada partial pressure'lardan bahsediyorum. Tamam. Güzel. When dealing with gas mixtures, okay, the partial pressures also need to be known for a complete description of the state. Okay, and this is given by Dalton's partial pressure law, which states that in a mixture, each gas has a partial pressure of its own, as if that gas is single in a whole volume of the system. Okay, just like as if it is a single. This does not interact with any other molecules. This is a perfect gas law. Okay. So what about real gases? Okay. So far the observations of all the laws are based on either pressure, the limiting case where the pressure goes to zero, or a perfect gas where there is no real interaction, where there is no intermolecular or other interactions. Okay, in real life, there is no such gas actually. Okay, especially when you lower the temperature and when you increase the pressure, we do see interactions of molecules with each other. Okay, that actually that causes deviation from the ideal gas law. And as you see over here, if this was a perfect gas, we would not see any potential energy, because for the perfect gases, we assume that they are not interacting with each other. Okay, But experimentally, we see that when we look at the reaction coordinate versus the potential energy, we see some potential energy when the molecules come closer to each other. That is caused by the repulsion of the molecules. And when you increase the distance between molecules, we do see some attraction too. Okay, at over very large distances, we don't see any interaction, which is just obeying the ideal gas law. Okay, so for real gases, instead of PV equals to RT, now we have a term Z, which means the compressibility factor, okay, which is given by the real volume of the system divided by ideal volume of the system. Okay, so the real volume of the system can be more than the ideal volume or less than the ideal volume, depending on the condition. Okay, as you see over here in this picture, you see that the compression factor is sometimes less than 1, sometimes more than 1. In ideal gases, the Z is equals to 1. Okay. When we increase the temperature or when we lower the pressure, what we see is that, when we increase the temperature, repulsions dominate, which means that Z becomes more than 1. Okay, and at low temperatures, the attractions will dominate and Z becomes less than 1. So the real will be either less or more than the ideal volume. Okay, we will actually talk about the nature of this real volume. Slide tam ekran yapabilir misiniz demiş arkadaşımız. Şöyle yapayım ve şuradan da tool'u nasıl gizliyorduk? Tamam, tüm ekran yaptığım zaman arkadaşlar buradaki, onu da deneyelim. Şöyle yapalım bir saniye. Şunu. Evet, ama burada. Tabii burada. Okay, now are you seeing better? Okay. Let's look at the participants now. Okay, so when we define a new, when we introduce this deviation of compressibility to the ideal gas law, we get a virial expansion, okay, and virial equation of state. So in which the PV now is R times T times 1 plus B over Vm and etc. It's going, but we generally neglect the higher order terms because the V square gets too large and this contribution of this whole values are very small, and we approximate this to as only this part. Okay, if the pressure goes to 0, so Vm goes to infinity and it goes to all terms over here will be 0, and this equation becomes just like an ideal gas. Okay, so B equals to 0, it's already ideal. This equation of state, virial equation of state, can be also expressed as pressures instead of the volumes in this picture right here. See? Okay. There is another actual deviation from the another definition to the state of the system, the equation of the state of the system, which is van der Waals equation. So instead of having just compressibility factor, now it tries to explain or to explicitly put deviation terms in the ideal gas equation and correct ideal gas equation for real gases. Okay, it has two parameters both of them are derived from molecular concepts. The first, it assumes the molecules are spherical, hard sphere molecules. Okay, molecular shapes is always spherical, and then so for each molecule, the volume it occupies is actually 4/3 pi r cube, and actually a statistical term for each contribution from each molecule in an n molecule system is given by a constant value of B. This B is actually the volume the molecules occupy in space. In ideal gases, we did not have any volume. Okay, that's why the whole system's volume was assumed as the volume, no matter how much gas molecules put in this volume, the volume stays the same. But in this case, each molecule covers a space in this container, and collection of these whole molecules will actually reduce the total volume by some amount. Okay, this reduced amount is given by B. And now the pressure, instead of having an RT over V, now we correct the term V. Instead of saying V, we now say V minus NB, because this amount of volume is already filled with the molecules, and that cannot be used as a free degree of freedom that the molecules can hang around. Okay, because the molecule sizes already fills this space. There is also a second term in which the molecules actually do interact with each other. Okay, but when they come too close to each other, they repel each other. When they go far from each other, they attract each other. Okay, when they are infinitely far away from each other, they do not have any interaction, which is the case in the ideal gas law. But now, as long as you don't go too much of pressure or too much of temperature, the gases do not come very close to each other. And repulsion term is a little bit out of topic here, because it can be neglected. It can be ignored for lower pressures. Okay, but the attraction term must be included, and that attraction term is given by this term over here. Okay, that attraction term brings when you have molecule hitting the wall. Okay, the molecule hits the wall, the other molecule attracts this molecule a little bit towards itself. That is why the collision of this molecule to this wall is reduced by the other molecules, right? The total pressure, that's why, is reduced by the attraction term of the other molecules on the molecules that are colliding the wall of the container. Okay, that is how van der Waals equation of state is generated, and the ultimate formula is given by this. Okay, did you understand that? Okay. Both A and B constants, they are constants in van der Waals equation, and they have units actually of this, and this. So there are some examples for you to see what amounts that we are talking about, okay? Excuse me. For helium, for example, helium is really very close to ideal gas, and it's almost zero, right? The attraction term is almost zero. This is very close to ideal gas. So in this equation, when you have A equals to 0 and B is small as possible, so the equation becomes just like this, which is the ideal gas. As you see, the helium among these is the closest to the ideal gas behavior. Okay, there are some other equation of states. For perfect gases, we know this one. For van der Waals, we know this one. There are other two equations of states that we haven't talked and we are not going to cover in this class, but I just wanted to put for you to see. And that is this virial equation of state. So these are the equation of state. That all these equations of state combine all four variables into a single formula. That means instead of defining all four variables, now I can define only 3 of them. The fourth one can be determined from using these formulas. That's why in order to describe the state of the system, what we need is among these variables, we need only 3 of them, because the fourth one can be determined from equations of states like these. Okay. Okay, now let's move on to kinetic molecular theory. This is a very important in chemistry because it explains the perfect gas law, which is the which is based on macroscopic gas laws or measurements. This is actually at molecular level, it brings an explanation why we observe this relation in terms of pressure and volume, why we observe the relation between the volume and temperature, etc. Okay, it also connects the microscopic level to macroscopic level, which is very nice to explain things. But since it is at molecular level, this is only theory. This is not a law. A law and theory is different from each other by only that if it is a law, that means everyone can experience it with themselves without having any hard time. Okay, it is easy to measure because it is a bulk system and everybody can measure that system. What in theory does not mean that it is not complete. No, it is still complete. It is a whole story, but it is really hard to measure such observations. Instead of measuring, we imply them. That is why we don't really, not everybody can experience it on their own. That's why we call these theories. So the kinetic molecular theory is actually is very important in explaining other chemistry laws. Okay, there are 3 different assumptions that the kinetic molecular theory uses. First, the gas consists of molecules of mass in ceaseless random motion, obeying the laws of classical mechanics. What does that mean? The gas molecules will move randomly and will not stop forever. Okay, and they do obey the classical mechanics. What I mean, the Newtonian physics, F equals m times acceleration, right? Mass times acceleration. The second, the size of the molecules is very, very small, so small that it is negligible. We can ignore the size of the molecules. That's why they do not occupy any space, any volume in the space. They do not occupy any volume in the space. And since they are very small in size, their diameters are really, sorry, their diameters are very small than the distance they travel in the container. Okay. So that is why, that is also another explanation that since these are very small each others, their size is very small, there is no interaction between molecules. They have infinitely far from each others. Okay, this is another assumption of the kinetic molecular theory. And the third one is the molecules will actually collide with each others in a way that they keep their motions elastically. The collisions occur elastically. Elastically means that if this has a velocity, this has another velocity, the velocities can be exchanged between these molecules, but the overall kinetic energy will be the same. Okay? And the molecules actually goes in lines, not wave motion. They do go in lines. This is another assumption of kinetic molecular theory. When we set these assumptions, when we understand these assumptions, the following will be easy to understand. So first we have to distinguish between the speed and velocity. Speed means the rate of change of its position. Speed does not have plus or minus or directionality. It has just magnitude. But velocity is the direction of travel as well as the rate of motion. Okay? So when velocity has a vector is a vector actually, and it's combined by in three-dimensional space, it's combination of x, y, and z components. And linear momentum is given by m times velocity, mass times velocity. So this has also a vector-like property. This is also another vector. Acceleration is F equals to ma. This is what you already know. But because mv is the linear momentum and a is the rate of the change of velocity, so we can rephrase force as the momentum change over time. Okay? If there is no force applied on a system, the momentum of this whole system over time will not change. This is called conservation of the momentum. Okay? This is very important aspect of classical physics. So let's assume that the pressure is formed by the total force of molecules colliding the walls of the container. Okay, as you see, this molecule is just before collision. It has a velocity of Vx. Just assume it's one-dimensional, it's only x direction. So it has one mass times Vx is the momentum. But after collision, it will change the direction and it will have negative momentum. Okay, so the momentum change before collision and after collision is given by this formula, right? And the distance it travels in just delta t amount of time is given with this formula. So let's now build our three-dimensional box. And the distance over here it travels. So let's assume that the molecules in this distance can make up to the wall. Okay, they can reach at this wall of the container. So for n molecule and three-dimensional system, the volume of this right here, the molecules that can reach to the wall, is given by this formula. only the number of molecules within this volume actually can reach to the wall. Actually, when we give the number density of molecules within that volume, is this volume over total volume, right? So this volume over total volume and the number of total molecules will give me the number of molecules that are in this amount of volume. Okay, and actually when we consider the system, the molecules within this volume will have some of them are in any instant time, some of them will have just collision occurred, some of them will have collision did not occur. So half of them will go this way to the wall side, the other half will go to the other side, right? That is why the number of molecules that hit the wall, that hit that wall, that behind wall, is given by this formula. This many of molecules will hit the wall, okay? So the momentum change of all molecules hitting the wall is given by this, okay? Therefore, so we can just rephrase this mass times NA as molar mass. We can replace this, and we can derive this formula as the momentum, the force. We define the force as the momentum change over time, and we put this in the formula, and we see that the delta T's will cancel out, okay? And what we have is only this part of the equation. So this is corresponding to force. Now we also need the definition of pressure, which is given by force divided by A, the area of the wall. When we put that formula, the area will also cancel out, okay? So we should also know that not all the molecules will have the same exact speed. They will have different speeds, different individual speeds, but the overall, their kinetic energy will be the same, or the overall, their average speeds will be the same. That's why instead of writing V squared, we just should put a bracket over here to show that it is average value, okay? So the pressure is now given by this formula, and the average values of x squared, y squared, and z squared are all the same, because you see from here the gas molecules. Oops, where is my? Okay, here. The gas molecules they will not hit only the this side, they will also hit the other side. So they will have the same exact collisions. And we can rephrase V squared as the combination of x squared, y squared, and z squared, and give this combined value as the 3 times of only x squared, right? So we can write 3 times x squared, the Vx squared is the actual V squared of the molecules. So if we define VRMS, which is the root mean square speed, by this formula, the square root of the total velocity squared, now my equation becomes like this: PV equals 1/3 and molar mass times VRMS squared. So since the velocity is only dependent on temperature, at constant temperature, the right-hand side of this equation, this side of the equation will be constant. So at any constant temperature, PV will be constant. Okay, this is actually what Boyle found using totally macroscopic properties. Now we derive totally from molecular approach. We used we used kinetic molecular theory approximation, which has 3 assumptions, and we derived the same formula, okay, as the Boyle's law. So when we combine this finding to the ideal gas law, we can see that VRMS is given by this formula. Okay. So if we extend this to another, if we try to understand the time of arrival, I mean, we can extend this formula in terms of times of arrivals of the same distance. We can relate that each molecule will have their molar masses, relative the molar masses square root. Okay, this is actually how the mass spectrometers work, and you are actually going to be asked questions about this and this final ultimate formulas. There is one last extension to that, which is actually the average kinetic energy, which is given by 1/2 mass times VRMS squared, which becomes now 3/2 RT. So the average kinetic energy of the system is only depending on the temperature, which is due to the speed of the molecules. Okay, this was the end of my class today. Yes, if we had time, I would show you the, yes, let's stop it over here, okay? I'm not going to continue more because I do have some topic to cover, but right now I don't think it's a little bit too much to you now. Okay. Is there any questions regarding this? Do you have any questions, ladies, gentlemen?
Hocam benim bir sorum var ama kitapla ilgili.
Buyurun.
Hocam kitapta sizin önerdiğiniz bir tane kitapla, yok, önerdiğiniz 3 tane kitap var. Bir de ders için textbook var. Ama hangisini kullanmam gerekiyor? Hangisinden ilerlersem daha iyi olur?
Arkadaşlar share'i kapatıyorum. Şimdi şöyle, ben 3 tane kitap önerdim. Siz bioengineer'lar olduğunuz için 3 tane, birkaç tane ekstra kitap önerdim. Yani bazen onlara temas edeceğiz ama daha çok Atkins'in kitabı arkadaşlar. Atkins'in 11. edition. Zaten dersimizin, bu online dersimizin de kapağını oraya yapıştırdım resim olarak. Daha çok bu kitap üzerinden gideceğiz. Bu kitabın e-book'unu da zaten attım size. Kitapları satın almak zorunda değilsiniz ama bu Atkins'in kitabını arkadaşlar ben tam 3 tane ders için kullanıyorum. Yani çok kapsamlı bir kitap ve çok ben güzel buluyorum, akışkan buluyorum. Biraz fazla detay var, evet. Daha çok kimyacılar ve fizikçiler için dizayn edilmiş bir kitap. Yani siz bioengineer'larsınız, size göre anlatmam gerekiyor, doğru, ama ben de kimyagerim ve fiziko-kimyacıyım. Çok da fazla ancak o kadar yaklaşabileceğim. Yani bazı konular olacak, sizi ilgilendirdiği için sırf Tinoco ve Atkins'in Life Sciences kitabına temas edeceğim. Ama daha çok Atkins'in orijinal kitabından gitmeye çalışacağım arkadaşlar. Atkins'in 11. edition, Atkins Physical Chemistry. Kitabımız temelde bu olacak arkadaşlar.
Hocam teşekkür ederim öncelikle. Bir de sınav için kitapta çıkacağını söylediniz. O zaman Atkins'e mi çalışalım?
Yani sınavda 3 kaynaktan da çıkabilir. Yani şimdi derste işin biraz daha, ben mesela hiç örnek çözemiyoruz gördüğünüz gibi. Ders çok yoğun geçiyor, geçecek de. Belki bir uygulama koyarız sınavdan önce. Ama dediğim gibi sınavda bu 3 kitaptan olacak. Ama daha çok Atkins'ten olacak, evet. Yani 3 kitaptan da sınav soru gelebilir. Kitapta olmayan bir soru da gelebilir. Yani biz kendimiz kafamızdan da soru yapabiliriz. Ama neticede daha çok etkin sağlıklı olacak ve etkin diğer hepsine hakim olacak yani. Slaytları dersten sonra paylaşacak mısınız demiş Zehra Elif. Evet, isterseniz paylaşabilirim. Sisteme yükleyebilirim. Başka sorusu olan var mı arkadaşlar? Şimdi ben daha önce size MIT'nin sitesini anlattım, değil mi? Thermodynamics and Kinetics diye bir ders vardı MIT OpenCourseware'de. Oradan da takip edin arkadaşlar. Gelecek hafta kinetik moleküler teoriyi bitirip termodinamiğe giriş yapmaya çalışacağız. Gelecek haftadan itibaren orayla daha şeyde gidebiliriz. Bakalım. Orayı da takip edin. Oradaki videoları da takip edin arkadaşlar. Tamam. Teşekkür ediyorum arkadaşlar. Şimdi kaydı durdurmamız mı gerekiyor? Nereden durdurmamız gerekiyor? Onu da bilmiyorum. Şuradan kaydı durduracağım. Ben arkadaşlar hepinizin çıkmasını bekleyeceğim. Daha sonra ben çıkacağım.